Chapter 6, Introduction to Continuous Probability Distributions. So recall in Chapter 5, we focused on discrete random variables, things that we can count. In Chapter 6, we'll be focused on continuous probability distributions. These are random variables that you cannot count because they include all possible numbers down to the decimal. So in this video, we'll be focused on the normal distribution as well as the standard normal distribution and how we can use that information to determine the probabilities of something occurring. Here we have our normal probability distribution curve. What this states is that all my random variables fall within this bell-shaped curve. Note that the probability on either side of our curve is 0.5. And when I add 0.5 to 0.5, I get 1. We learned in Chapter 4 about probabilities and how the sum of our probabilities will equal to 1. So we see that here in our normal probability distribution is that the probability of all of our possible random variables will equate to 1 under this curve. Now there are some characteristics that we should be aware of in terms of the normal probability distribution. It is symmetrical in that the distribution on one side of our curve is the mirror image of the other side. Hence, they're both 0.5. It is unimodal in that there is one peak or a single mode. Our mean, median, and mode are equal. And the amount of variation in the random variable determines the height of our curve and the spread. So how high and how wide our curve goes. One last thing is that our curve is asymptotic to the x-axis, meaning our curve right here never touches the x-axis. Now there can be different normal distributions based on our population mean and population standard deviation. When our mean shifts, our distribution will either move to the left or to the right. And if our standard deviation increases or decreases, that will affect how wide our spread is. So we can see here that we have 3 different normal distributions, and while their shapes differ depending on their standard deviation and where the mean falls, the area itself is the same in all 3, because the area of any normal distribution is a total of 1. And if we split it in half, half of our area is on one side and the other half of the area is on the other side. Here's the normal probability density function. This is the function or formula that you would use to find a particular value of a continuous random variable. Be aware though that we are not going to use this formula, because if we were to look for a specific value of x, our probability of getting exactly that number is going to be 0. Instead, when we look for normal probabilities, we're looking for the range of values between 2 numbers. And so when we're looking for the range, as you can see here in our normal distribution curve, we're looking for the area under the curve. And you might remember from previous math classes when we're trying to find an area of something, there's different formulas. For instance, in the area of a square, or the area of a rectangle, or the area of a circle. But as you can see here with our curve, it is not easy to necessarily find the area of this particular shape. In order to find the area within our normal distribution, we will convert our numbers into standard normal distribution and use an appendix. Any normal distribution can be converted into a standard normal distribution or z-value. You did this in Chapter 3. If I take a particular x and I have my mean and my standard deviation, I can convert it to a z-value. The z-value is the scaled value or the number of standard deviations that x is from the mean. Our normal distribution has a mean of 0 once it's converted and a standard deviation of 1, and we can go up in increments of 1. The horizontal axis here is in z-values, and anything above the mean on the right side here will be positive, and anything on the left side of my mean will be negative. So x is any point on our horizontal axis that we want to convert into a z-value. So to use the formula, you'll identify an x, a particular point on the axis that you're interested in converting, and we've got our mean for a particular distribution, and you'll need your standard deviation. Here's our example. If x is distributed normally with a mean of 100 and a standard deviation of 50, what is the z-value when x equals 250? So down here below, you'll see I've got my normal distribution curve right here, and our x values state that our mean is 100. So my midpoint right here is 100. Our standard deviations are 50, and we want to convert our x of 250. So we'll plug in our numbers where x is 250, my mean of 100, and my standard deviation of 50. When I plug that into my calculator, we get a z-value of 3. Our x of 250 is 3 standard deviations, or 3 increments above the mean of 100. As you can see, it's easier to talk about how many standard deviations away a particular number is, as opposed to talking about the specific x values. This allows us to compare different types of information using a standard language. This also makes it easier because once we have standardized our values into z-values, we can use an appendix to figure out the probability of something happening. So in your textbook, we have the Appendix D, which provides the probabilities for our standard normal distribution. The way our appendix works is it looks at the area from the mean or the middle of our curve out into the direction of our z-value. So to read it, the numbers here on the left under the letter z, the row shows the value of the z to the first decimal point. So for instance, here we can see the z-value in our little curve here is 1.25. So I would go to my z and look up 1.2, which is right here, because it's going to go up to the first decimal point. And then to get to the area, I'll look at the column values, which gives us the second decimal point. In this case, the second decimal value in our z-value here is 5. So I'm going to go across till I get to 0.05. In other words, I'm adding 1.2 plus 0.05 to get my 1.25. And this 0.3944, that's the area that's shaded here in the curve. Note that if you go online and Google standard normal distribution tables, some tables will look like this, where it gives you the probability from the mean to your z-value, but other tables may be cumulative, meaning they'll give you the value from left all the way to right. And that's also how it's done in Excel. So just be aware that there's different ways to set up our standard normal distribution tables, but the one I'm showing you here is the one specifically for our textbook. So the steps to go through our normal distribution, the first thing we want to do is find our mean and our standard deviation, and then identify our event of interest. What is it we're trying to find the probability of? Then you'll convert the random variable into a standardized z-value. So I'm going to change my x's to z's, because once I do that, I can now go to the Appendix D and find the area or the probability within my curve. Remember though, it tells me the area from my mean to the particular z-value I'm looking for. And then based on that, knowing that our entire curve is worth 1, or either side is worth half or 0.5, we can then determine the probability of the area we're interested in finding. So we're going to look at several examples or scenarios in which we would use our appendix. Suppose x is normally distributed with a mean of 8 and a standard deviation of 5. We want to find the probability that our continuous random variable is between 8 and 8.6. So you can see here in our curve, in black are our x values, where 8 is our mean, so that's our middle. And we want to find the probability between 8 and 8.6. So this shaded area right here. So to do that, we have to convert our x's into z-values, because then that will allow us to look at the appendix. So I'm going to take my x of 8 minus my mean of 8 and divide it by my standard deviation of 5. Thus our z-value for our mean of 8 is 0. We also have to convert our 8.6 into a z-value, where my x here, my 8.6, minus my mean, divided by my standard deviation gives me a z-value of 0.12. So if we look down here, we can now see how I've converted my x's into z's. This will now allow me to go over to the appendix, and I've got a snapshot here of the Appendix D for the values that we care about. We're going to look up where z-value is 0.12. So I first look up to 0.1, and then I'll go across the columns until I get to 0.02. So right here at 0.12 is 0.0478 shown. All that means is the area here between my mean and the z-value to the right is 0.0478. So the probability that I'm going to get some number between 8 and 8.6, or between the z-values of 0 and 0.12, is 0.0478, or 4.78%. Let's look at another example. So we still have our same distribution, but now we're interested in finding the probability that x is between 7.5 and 8. So again, I'm going to convert my two x's into z-values, where I take my x of 7.5 minus my mean divided by my standard deviation, and my z-value is negative 0.1. So we can see here negative 0.1 is my z-value associated with an x value of 7.5. The negative just tells you I'm going to be on the left side of the curve. When I calculate the z-value of 8, or my mean, we know that's 0, so 0 is right here for our z-value. And now I can go over to my appendix, because what I want to do is find the area of the shaded space from the mean. Note though that the appendix does not show any negative symbols, because the negative sign just tells you that I'm on my left side. What we're really interested in with the appendix is the area, and you can't have a negative area. So you'll just look up the 0.10 on our table. So I'm going to go over here to 0.1, and because my second value is a 0, it's going to be this column right here that shows 0. So this shaded area in brown, according to our table, is 0.0398, or 3.98% chance that my x value will be somewhere between 7.5 and 8. Here's another example. Now we're looking at a shaded area that spans across both sides of my standard normal distribution curve. Assuming our mean and standard deviation are still the same, now we want to know the probability of our variable occurring between 7.5 and 8.6. Now, in our previous slides, we already converted our x's into z-values, so we've already done the math. I won't take too long on it. And again, with our z-values, we know how to look it up on our appendix. We'd already identified that the probability of each shaded area is 0.0398 and 0.0478. But we want to know the total shaded area. So to do that, we would add the two numbers together. We'll add 0.0398 and 0.0478 to get a probability of 0.0876, or 8.76%, that my x will be somewhere between 7.5 and 8.6. Here's another example. Our mean and our standard deviation are still the same, but now the probability that we're asked to solve is the probability that x is less than or equal to 8.6. That means we're looking for all numbers smaller or equal to 8.6. We only have one number we need to convert here into a z-value. And we already did that on the previous slides, where we took our x of 8.6 minus our mean and divided by our standard deviation to get a z-value of 0.12. Using our appendix, we know that the shaded area between our mean and our z-value of 0.12 is 0.0478. But that only gave us this part right here. So to find our total value of all random variables below 8.16, we then have to look to the left, below. We'll go to the left side. And we know that on this side of our curve, it's worth half. So that's 0.5. Now we'll total up all of our shaded areas, and that will give us our probability that x is going to be equal or less than 8.6 by taking 0.5 and adding 0.0478 to get 0.5478 or 54.78% chance that we will get an x value that's less than or equal to 8.6. And we want to now find the probability that x is greater or equal to 7.5. Recall we've already converted 7.5 into a z-value, so we know it's negative 0.1. And using the appendix, we know that the area between our negative 0.1 and our mean is 0.0398. That only gives us this sliver of shaded area here on the left side. If we're looking for an x value greater than 7.5, meaning all numbers to the right here, I now need to add this half of my curve. When I add the two numbers together, 0.0398 and 0.5, that gives me my total shaded area, or my probability of getting a value that's greater or equal to 7.5 to be 0.5378 or 53.78%. Say we're looking at the same problem again, but our shaded area is not touching the mean. We already know what our converted z-value is, and we know that the area between the z-value and the mean is 0.398 according to our appendix. So in order to get the shaded area, since I know half of my curve is 0.5, I'm going to get the shaded area by subtracting what I do know, that's this area here in white, from my half of the curve. So my shaded area is 0.4602. Similarly, whether you're on the right side or the left side, same process, where we've already converted what our x value at 8.6 is for our z. So we already know it's 0.12, and that the area according to our appendix in here between our mean and our z value is 0.0478. But I want to know the shaded area, so greater than 8.6. So here again, I'll take my 0.5, because I've got half my curve, subtract the area I don't want, and that gives us 0.4522 for my shaded area here on the right, or what's greater than 8.6. Let's do a practice problem on your worksheet. Say we've got a population that's normally distributed with a mean of 100 and a standard deviation of 20. You're going to be asked to find several probabilities here in parts A, B, and C. So in part A, you're asked to find the probability that x is greater than 130. I find drawing the curve is helpful for me to organize my thinking, and I can see the shaded area that I'm looking for. So my mean is 100, so that's my midpoint, and my x is 130 or greater. So I can draw 130 right here, and greater is going to be to the right. So I'm looking for this shaded area here. But in order for us to use the appendix, we have to convert our x of 130 into a z. So I take 130 minus the mean divided by standard deviation. That gives me a z value of 1.5. So now I can see my z value here for 130 is 1.5. Then I'll go to my appendix, look for my z at 1.5, and I do not have a second number, or it represents 0. So I'm going to look at this number right here of 0.4332. So that's what the appendix tells me for the area between my mean and my z value. But that's not the value I want to know. I want to know the shaded area. Since I know this half of the curve is 0.5, I'm going to have to subtract my area found from the appendix from 0.5 to give me the shaded area at 0.0668 or 6.68%. In part B, it's asking us to find the probability that x is less than 90. So again, if I draw my curve, mark my mean in the center, and I identify where 90 potentially falls. It doesn't have to be perfect, it's just a rough sketch, so I know which side of the curve I'm on. Again, I'm going to convert my x value into a z value by taking 90 minus 100 and dividing it by 20. That gives me a negative 0.5 for my z value. The negative tells me I'm on the left side of my curve, just so I'm in the right direction. And I'll go to my appendix and find my z value at 0.50. So here's my 0.5, here's my 0, the second value in my z value. and that gives me 0.1915 right here between my mean and my z-value. But again, that's not what I'm interested in. I want to know the probability of the shaded area. Since I know that this half is worth 0.5, to only get the shaded area, I will subtract what I know from my appendix, 0.1915, from 0.5, and so the shaded area is 0.3085, or 30.85%. Last time, Part C asked us to find the probability that x is going to be between 90 and 130. So here I'm mapping my x's between 90 and 130, and I know my mean is 100 because I'm given that in the problem. The nice thing is we've already calculated the z-values in Part A and Part B for 90 and for 130, so that saves us some time. And we looked at our appendix and we know the value of the shaded area between the mean and the z-value. So our appendix told us that our z-value at -0.5 is 0.1915, and our appendix told us that the area for our z-value of 1.5 is 0.4332. Now, since I want to know my shaded area here, I will have to add my two numbers together. So when I add 0.1915 to 0.4332, that gives us our total shaded area, or our total probability, at 0.6247, or 62.47%, that my x values will fall between 90 and 130. So as you can see, when we're working with a standard normal distribution, there's a little bit of math, there's a little bit of the appendix that we're going to use to help us find the probability or the area of something occurring, and we have to use critical thinking to know how to apply the appendix accordingly, whether we're adding or subtracting, are we on the left side, are we on the right side, and this takes a bit of practice. So let me know if you've got any questions or concerns.